Hi everybody. So again, I'm going to do a little warm up before we start really getting into, the thick of things. So just maybe as a reminder, I posted the first homework yesterday. It's due next Friday by midnight or 11:59, whatever. I also made a Discord server for the class if you're interested in that kind of thing. Mostly because, well, I'm already basically always on it because I'm at home, not going anywhere, and I have my computer in front of me all the time. And it can act as like a low-key sort of office hours type deal. And that you can always just pop in, ask me a question. Hopefully I'll get back to it relatively soon. If you don't feel like waiting another week to my office hours. All right, so this warm-up. I'm going to define three topologies on the real line in terms of bases, which we now know from last lecture. So the first one, definition, is the standard topology. So it has, as a basis, or one of its bases is all open intervals. And, well, the name open is kind of suggestive. You may have learned this before in a different class, but these are all intervals of the form A, comma B, where A and B are positive real numbers, are real numbers. Just to be precise, this set actually, consists of all reals x. My handwriting is the worst. Such that x is strictly between A and B. So when you see me write just, the reals with no implied topology, just think about it as the standard topology. If there's some kind of non-standard topology, I'll always kind of clarify that. So, in particular, the lower limit topology on the reals has basis all half-open intervals. So again, A is less than or equal to B. And when I consider the reals with this basis or with this topology, I'll write it as R subscript L. It's supposed to be like a script L. It's a fun little note. You can actually recover this symbol in LaTeX as, I don't remember if it's which direction the slash goes, slash ELL. Sometimes the reals with this topology are called, this is a stupid name. It's called, well, I shouldn't say it's stupid. It's somebody's actual name. It's the Sorgenfrey line. The fact that it has a different name should imply, which we'll see in a sec, that this is actually a different, distinct topology than the standard topology. Lastly, the one we'll be talking about will be the K topology. It has basis. All sets are all subsets of the form. You take an open interval, just as before, and you subtract a certain set K from it, where K consists of the sequence 1 over n, where n is a positive integer. And we use the notation R sub K for this topology, this topological space. All right, so why am I doing this? Well, it's kind of a fun little thing to see that maybe this is just a proposition. The topological spaces, or maybe the topologies on the lower limit topology and the K topology, or topologies, I should say, are strictly finer than the standard topology. And moreover, the lower limit and the K topology are not comparable themselves. The exclamation mark is not part of the theorem, it's just something I'm adding. So I haven't necessarily talked about strictly finer. That means that it's, in particular, it's finer, and that there are some sets that are open in these topologies that are not open in the standard topology. So proof. Well, we take some basis element of the standard topology. So maybe I'll call the topology here tau prime, tau double prime, and tau. So this is a basis element in tau. And let x be some element of this interval. Then, well, this is not, it is open in tau prime, in the lower limit topology, right? By definition, it's open, it's a basis element. But the point, what the fuck was that? The point x in this set has no open neighborhood, I should say. No basis. In the standard topology contained in x comma b. So it's strictly finer than the standard topology. So that means they subset, but not equal to. Likewise, in the K topology, well, if we're away from, the set K, this is a basis element of tau, and it's also going to be open in, so this is in tau, and it's also going to be in tau double prime. However, there's one particular element that's a problem. So maybe we'll take something like an open set -1 to 1. Then I will subtract the set K from it. So this is definitely 100% in tau double prime. And, well, 0 is an element of this set. So maybe I'll draw this, see what's going on. Here's 0. Here's the set K, right? It's the sequence 1 over n. And let's do blue. -1, and this is 1. I got the sniffles leaking onto my iPad. So the problem here is that this whole thing is open in tau double prime, but it's not going to be open in the standard topology because there's going to be no open interval in the standard sense around 0 that's totally within this set, right? Because any open interval around 0 will hit infinitely many points of k. And so we're kind of screwed. So it's going to be not open in tau in the standard topology. To see why they're not comparable, why tau, so what did I just prove here? We proved that tau is a subset, but not equal to tau double prime. So, leaking. To see that they're not comparable, note that this is always going to be open in tau prime, but not in tau double prime. And likewise, oops, let's go over here. R minus k, the whole real line minus the set k, is going to be open in tau double prime, but it's not going to be in tau prime. So they're not comparable. There are some sets that are straight up not open in either of the two. All right, and that's our little proposition. Something kind of weird, non-standard, to get used to working with weird and non-standard things in topology. The theme of today later on will be the ordered topology. All right.